Hello everybody, and welcome to the very first math video on this YouTube channel. Today, we're going to be doing something really interesting, deriving the formula for the antiderivative of the absolute value of any function. Now, I was inspired to make this video after I derived the formula, but couldn't really find any information on it online, so I thought I'd make this video and share my findings with y'all. I first discovered this formula while working on a problem Black Pen Red Pen was working on, which was the antiderivative of the square root of sine squared x dx. Now, in that video, he was unable to come up with a solution to this problem. However, he did mention that the answer would be negative cotangent x, absolute value sine of x, plus c. So with the formula we'll be deriving today, we'll be able to plug in sine of x and get this answer out. If you'd like to check out that video, I'll have it linked in the description below, alongside some timestamps in case you want to skip ahead in this video. But we're going to get started by going over what the absolute value function is. Well, the absolute value function has a piecewise definition where we get the input back where the input is greater than or equal to 0, and the negative input back where the input is less than 0. So what the absolute value function is doing is it's taking its inputs and returning the non-negative version of that input. So what does that mean? Well, that means that anytime the input is 0 or positive, as in not negative, we can keep it the same. But anytime it is negative or less than 0, we have to multiply it by -1 because a negative times a negative will be switched to a positive and therefore not negative. So all the output values will be strictly positive. And to show that, I'm going to graph the function out. So at 0, we're defined as 0. And then from 0 to infinity, we get x. And from 0 to negative infinity, we get negative x. All right. We get this V shape, and it's important to note that at 0, there is no derivative because we have this sharp turn. Okay, it's nice that we have this piecewise definition, but it'd be even better if we also had an algebraic definition so that we could manipulate this function in different ways. Luckily, there is an algebraic definition. We get that the absolute value of any input is equal to the square root of the input squared for all real numbers. And why this works is because the squaring function outputs strictly non-negative values as well. So 2 squared will be 4 and -2 squared will also be 4. And then the square root just acts as the inverse to the squaring function. So we get back to our original value, but the non-negative version of it. Okay, very nice. There's one other function that I'd like to go over, and that is the sine function. Not the trigonometric sine function, but rather sine spelled S-I-G-N. This function also has a piecewise definition where we get 1 back if the input is greater than 0, 0 back if the input is equal to 0, and -1 back when the input is less than 0. So what's the point of the sine function? Well, it does as its name implies, and it returns the sign of the input. So for instance, if the input is positive, we want to return a positive constant. If the input is 0, we want to return a 0 constant. And if the input is negative, we return a negative constant. Okay, so let's graph this function out so you can see what it looks like. At 0, we just get 0. From 0 to infinity, we get 1. And from 0 to negative infinity, we get -1. So there's this jump here at x equals 0 from -1 to 1. Okay, it's nice that we have this piecewise definition, but once again, we like to have an algebraic definition, and luckily, we can just barely squeeze by with one. If you notice, the domains on which the absolute value function and the domains on which the sine function are defined are related to each other. They're not the same, they're related. As you can see, the absolute value function has a domain where x goes from 0 to positive infinity. Same with the sine function. Absolute value function has a domain where x is defined from 0 to negative infinity, so does the sine function. So the way that we get an algebraic definition from the sine function is by translating from the absolute value function's piecewise function to the sine function's piecewise function. Okay, how we can do that, one way, is to divide the output of the absolute value function by the input. So here we get x over x, which is equal to 1, where x goes from 0 to positive infinity, which is exactly what we wanted. And this one goes from, this one equals negative 1 from 0 to negative infinity. And that's exactly what we wanted. So let's write that out real quick. Sine of x equals the output of the absolute value function divided by the input. Okay, there's actually another way that we can write this function, and that is by taking the input and dividing it by the output of the absolute value function. As you can see, we'll get 1 and negative 1 once again. So let's write that out. It's equal to the input over the absolute value of the input. And now notice that these two definitions are the reciprocal of each other, so we can write that this is all equal to the reciprocal of the sine function. Now, it's important to notice that this algebraic definition is not defined for all real numbers. Here, in the denominator, we have the possibility of dividing by 0. And so we have to go back to the piecewise function whenever we're trying to evaluate the sine function at 0. Okay, there's one more property that I want to mention real quick, and then we can move on to derivatives. I'm going to take this first definition right here and multiply both sides by x. So we'll get absolute value of x equals x sine x. Okay, so I've written our properties on the left side over here, and now we can start with derivatives. So we're going to start with the derivative of the absolute value, and then we're going to move to function notation. So the derivative of the absolute value of f of x, we can rewrite using this first property is equal to the derivative of the square root of f of x squared. Now here we can just use chain rule to evaluate this. So derivative of the outside, we'll get 1 over 2 square root f of x squared times derivative of the inside, we'll get 2 times f of x times f prime of x. And now I'm going to rewrite this square root of f of x squared as the absolute value of f of x. These 2's will cancel out, and we'll have f of x over absolute value f of x times f prime of x. And now this left-hand term, this f of x over absolute value f of x, is actually going to be equal to the sine of f of x from that second property. So we'll get that the derivative of the absolute value of any function is equal to the sine of that function times its derivative. All right, we can now continue with the derivative of the sine function. So the derivative of sine of f of x, I'm going to rewrite using the second property with the first definition. You could use the second definition, and you'll end up with the same answer. So I'm going to use this absolute value, the derivative of the absolute value of f of x over f of x. And now since we know the derivative of the top and the bottom, we can use quotient rule to evaluate this. So we'll get that this is equal to f of x, and then the derivative of absolute value of f of x is sine of f of x times f prime of x minus absolute value f of x times f prime of x. All over f of x squared. Okay, so I'm going to rewrite this f of x times sine of f of x using this third property, I'm going to rewrite it as the absolute value of f of x times f prime of x minus absolute f of x, f prime of x, all over f of x squared. And now notice that this left-hand side is actually equal to this right-hand side. So in the numerator, we're going to get 0, and that's going to leave our derivative equaling 0, which is strange at first. Normally, we think of the derivative of constants equaling 0. But this actually makes sense. When you think back to the piecewise definition of the sine function, note that for all of our domains, we're only ever outputting a constant. So the derivative at all those constants, the slope of all those constants, is going to be 0. When we ask what's the slope at any point on the sine function, there is no slope. So 0 slope is the answer. All right, so we now have everything that we need to find our antiderivative. So let's go ahead and take the antiderivative of the absolute value of any function f of x, and I'm going to rewrite it using this third property. We're going to get the antiderivative of sine of f of x times f of x dx. And now I'm going to use integration by parts here. So we're going to let u equal sine f of x, and we're going to let dv equal f of x dx. Now I'm just going to write the antiderivative of f of x as capital F of x, and then our du, the derivative of sine of f of x, is just going to be 0. Okay, so let's write this out. U times v is going to be sine f of x times capital F of x minus antiderivative f of x times du. Du is 0. So f of x times 0 is just going to be antiderivative 0. We're going to get that this all equals sine f of x times capital F of x. We'll write this as a constant, and there we have it. Our antiderivative of the absolute value of any function is equal to the sine of that function times its antiderivative plus a constant of integration. And there we go. All right, so we can now continue and show that this formula does in fact work. So let's do that with the problem that we started this video with, the antiderivative of the square root of sine squared x dx. So I'm going to rewrite this using our first property. We'll get the antiderivative of the absolute value of sine of x dx. And now we can just plug this into our formula and get that this is equal to the sine of sine x times the antiderivative of sine x, which is negative cosine x, plus c. Now, notice this isn't exactly the form that we saw our original answer in. All that we have to do is rewrite this sine function as the absolute value of sine x over sine x. And then we're multiplying by negative cosine x plus c. And now we can rewrite cosine over sine of x as cotangent of x, absolute value sine of x plus c. And there we have it. Right, it'd be great if that's where the video ended. However, it wouldn't be a math video if issues didn't arise. So let's talk about the issues of integrating the absolute value function over distance. And to do that, we're going to take the integral from 0 to 2 pi of a problem that we've seen multiple times today, the square root of sine squared x dx. Now we already know that this is equal to the integral from 0 to 2 pi of the absolute value of sine of x. So what can we do with that? Well, to find the actual answer to this problem, we should first start by graphing out our absolute value function. So to do that, the first thing you should do is graph the inside function. So let's do that. We're going to take this graph from 0 to 7. 2 pi will go about here. Pi will go about here. 2 pi, or sorry, no, this should be 3 pi over 2. And then pi over 2 goes about here, and 0 would be right here. So let's graph the sine function. From 0 to pi, we have this positive period. From pi to 2 pi, we have this negative period, and then we alternate periodically. Okay, now to graph the absolute value of sine of x, we take the graph of sine of x and keep it the same for all positive values, but multiply by -1 for all the negative values. So let's do that. From 0 to pi, it stays the same since we're positive, but from pi to 2 pi, since we're negative, we multiply by -1 and get the absolute value of sine of x. And then we continue with a positive period, and then it repeats periodically. Okay, so let's note a few things. This first area, where the absolute value of sine of x is equal to sine of x, means that the area underneath both of those curves is the same thing. So the integral from 0 to pi of sine of x dx is equal to the integral from 0 to pi of the absolute value of sine of x dx. And since the absolute value of sine of x repeats every, the period repeats every pi distance, we can say that the integral from 0 to 2 pi of our absolute value of sine of x dx is just equal to 2 of these first periods. So it's equal to the integral from 0 to pi 2 absolute value sine x dx. Okay, so with that, we can now rewrite this as the integral from 0 to 2 pi of absolute value sine of x dx equaling 2 integral 0 to pi of sine of x. And since we already know the integral from 0 to pi of sine of x being 2, it gives us the answer that 2 times the integral from 0 to pi of sine of x should be 4. So the integral from 0 to 2 pi of the absolute value of sine of x should be 4. Okay, this makes sense. We have a positive area here and a positive area here. We should have a positive area in total. Very nice. Let's clear this space up real quick. And now we can take our formula and see how that evaluates. Okay. So we should see that the integral from 0 to 2 pi of the absolute value of sine of x dx should be equal to the evaluation of negative sine x times cosine x, evaluated from 0 to 2 pi. Okay, so now let's plug these in. 2 pi going into sine of x is going to be 0. Sine of 0 is going to be 0, times cosine of 2 pi is going to be 1. 0 times 1, 0. Now let's plug in 0. 0 goes into sine of x. We get 0. The sine of sine of x is 0. Cosine of 0 is 1. 0 times 1 is 0. So 0 minus 0 equals 0. But this doesn't make any sense at all. We have positive area once again. So we should have a positive area. But it doesn't seem to be that way when we integrate our absolute value function using the formula. So this shows that the fundamental theorem of calculus does not hold for integrating absolute value functions. However, we can still say that this formula holds for the antiderivative. If you plug this in and you take the derivative, you're going to get the absolute value of f of x. So it's just something to keep note of when you're working through these problems. And that's a good place to stop.